Thank you for that introduction. I'm Jessie Yuan, and on behalf of myself and my co-authors, I'll be presenting VoicePilot. VoicePilot is the first work with humans interacting directly with an LLM-integrated physically assistive robot. Physically assistive robots, in conjunction with assistive interfaces, can enable individuals with disabilities and others who require assistance to perform a range of self-care and household tasks. This can help increase independence, well-being, and quality of life while reducing caregiver workload. For those with the ability to speak, LLM-based speech interfaces could allow individuals to naturally provide robots with both high-level commands and nuanced preferences or customizations. Existing works have presented frameworks and guidelines for integrating LLMs with robots in the context of high-level task planning and code generation. However, no prior works involve human subjects interacting directly with an LLM-integrated robot for physically assistive tasks. Consequently, they lack insight and guidelines on the human-centric considerations essential for using LLMs as assistive interfaces. The contributions of this work are as follows. First, we present an iteratively constructed framework for integrating LLMs as assistive speech interfaces for a robot. Next, we use this framework to integrate an existing LLM with a commercial feeding robot, OBI, and we evaluate the interface through a human study with 11 older adults at an independent living facility. Lastly, we present a reflection and design guidelines based on the findings of the human study. Our framework was iteratively obtained through the implementation and testing of 3 different versions. The first version was created from existing literature in the fields. In order to iterate on and evaluate this framework, we designed a speech interface for OBI, a commercial feeding robot, using OpenAI's GPT 3.5 turbo model. This interface was then used to evaluate the framework through pilot studies with lab members. The second iteration focused on improving the accuracy and consistency of the interface. Changes were demonstrated with members of the community at a local disability awareness event. The final iteration focused on increasing the system's ease of use. It consists of 9 components related to both prompt engineering and system rollout, which is the process of deploying the LLM-based speech interface and robot with users. The 9 components are as follows: environment description, robot functions, function applications, code specifications, safety, robot variables, instructional materials, user control functions, and finally feedback. In comparison to all related work, our framework moves beyond governing only prompt engineering, instead providing recommendations for designing the system as a whole in a user-centric way. For example, the instructional materials component was introduced because we found that users initially struggled with giving commands to the system due to uncertainty about what the robot could do. Similarly, we added the feedback component because we identified that users had difficulty knowing whether the system heard them due to delays in processing, which led to confusion and frustration. Next, to evaluate our final framework, we conducted a formal study with 11 older adults at an independent living facility. The participants ranged in age from 72 to 91 years old, with an average age of 81 years. First, participants were asked to complete 5 predefined tasks. One such predefined task was to feed yourself a bigger scoop of blueberries. Here's an example of how a participant completed this task using the LLM-based interface.
I will be a large scoop of blueberries.
After all the predefined tasks, participants were asked to complete a 7-minute-long open feeding session during which they were free to eat however they liked using the robot. At the end of the study, we asked participants several Likert items, as shown on the slide. For all items, 7 represented the highest rating. The results show that participants found the system easy to learn, simple to use, and enjoyable overall. Participants also felt in control, with one participant remarking, "What I liked was that it gave me a sense of control. For somebody who's in an incapacitated situation, that could be very important." Using the NASA TLX scale, where a score of 0 indicates the lowest workload, participants generally reported low workload across all categories, as seen in the figure. Both qualitative and quantitative data from our study demonstrate the success of our framework in creating a well-received speech interface for the OB feeding robot. Lastly, we conducted a thematic analysis on qualitative data obtained during the study to gain insight into the needs and challenges our participants faced when using the LLM-based interface. We compiled our findings into 5 design guidelines for creating LLM-based speech interfaces for physically assistive robots as follows: customizability, multi-step instruction, consistency, comparable time to caregiver, and social capability. First, interfaces should offer customization options to allow users to tailor commands based on their preferences. Users frequently use modifiers like faster or smaller to adjust robot actions. However, inconsistencies in how the robot responded to these requests caused frustration. Users also wanted the system to handle non-predefined commands, such as mixing food. The video shows 2 different participants attempting to mix 2 foods together during the open feeding session. The one on the left is successful, while the one on the right is not. While the LLM interface allows for greater customization outside of predefined functionalities, it should ideally work for all desired customizations. Additionally, since different users can have different expectations for how their customizations should be interpreted, the system should adjust its actions to match each user's needs. This can potentially be done through accurate sensing of the environment and learning individual preferences. On the other hand, users strongly appreciated when the LLM-based interface successfully handled customization, which underscores its importance.
I liked the flexibility that speech gave me in controlling the technology. I find it much less cumbersome and intimidating.
Second, interfaces should be able to execute multiple functions in sequence from a single command. This improves both efficiency and user comfort. Here's an example of a user giving a multi-step instruction.
Hey, Obi. Let me have some granola and some blueberries and yogurt.
Participants appreciated this capability, but some faced issues when the robot struggled to handle complex commands. Additionally, multi-step instructions can enable users to do other activities concurrently, such as watching TV or carrying on a conversation, because they can trust the robot to continue the task without constant input. Third, interfaces should execute commands with speeds comparable to that of a caregiver. For many, slow task completion can lead to fatigue, especially during feeding tasks, but some may prefer a less hurried experience. This was evident in participant quotes, with some finding the system too slow, while others favored the robot over a rushed caregiver. Quantitative measures of temporal demand similarly showed high variance. Therefore, it is important to increase efficiency to limit fatigue, while also matching caregivers' ability to personalize timeframes based on an individual user's needs and preferences. Fourth, interfaces should execute commands consistently. The LLM should produce the same output both when given the same commands across multiple runs and when handling commands that are worded differently but share the same intended robot behavior. This video shows how very different phrasings spoken to our interface lead to the same robot action.
Hey, Obi, scrape down the yogurt dish and give me a spoon.
Hey, Obi, scrape down the sides of the yogurt and give me a scoop. Hey, Obi, scrape down the sides of the yogurt bowl and then feed me a scoop of yogurt.
Hey, Obi. Scoop the side of the yogurt bowl and give me a spoonful.
Several participants in our study commented that the system sometimes struggled to reliably execute commands as they had expected. Consistency is key in building user confidence and trust with robotic systems, so extensive testing before deployment is essential. And finally, interfaces should be able to socially engage with the user while carrying out the assistive task to more closely mimic the role of a caregiver. Although physical assistance is the primary role of the robot, we found that social interaction also plays an important part in user satisfaction. Several participants noted that the interaction felt impersonal or wanted to converse with the robot.
You say things like, hey, good morning, Obi, and then give a command, or is it strictly command?
Integrating some form of social engagement could lead to a sense of companionship, thus increasing user satisfaction and acceptance. In summary, we presented an iteratively constructed framework for integrating LLMs as speech interfaces for robots, created and evaluated a speech interface for a commercially available feeding robot using this framework, and finally proposed design guidelines based on reflections from the study. We encourage researchers to adopt these guidelines and framework when integrating LLMs into speech interfaces for physically assistive robots. Thank you. I'd be happy to take any questions.
Thanks, Jessie, for the nice talk. If you have questions, please line up over there. I think we will have time for some questions.
Hi, this is a great talk. I was wondering, you mentioned that the users had a hard time sometimes instructing the robot and would sometimes say things that the robot could not do or did not necessarily understand the capabilities of the robot. You know, this is kind of a tough problem. The search space, it's similar to like using Google, right? The search space is kind of large, and the early days of using Google is quite difficult. And now some people have a better time using it, but then Google also kind of improved their algorithms to match what people are searching. How do you think about constraining the search space or giving guidance or some sort of mental model for folks in navigating the search space when interacting with LLMs? Even though the task here was almost already very constrained, you noted that there's still a lot of nuance in like how people wanted the task to be done. So I'm wondering if you have any insight on that.
Yeah, that's a really great question. Thank you. So I think part of what we did when we introduced, for example, those instructional materials is we gave users a lot of examples on how sample interactions with the robot might play out. And I think a lot of people tended to base how they interacted with the robot very closely off of those examples. And so that kind of offered its own way of constraining what they felt that they could ask of the robot. But we also, we wanted to kind of explore what people would try to do with the robot too. And so that's where it was, and so during the open feeding sessions, we kind of encouraged experimentation. And so that's where we kind of saw a little bit more of those failures.
Thank you.
Thank you.
Yeah, thanks, Jessie. If you have more questions, you can also like discuss in the poster discussions. So thanks, Jessie.
Thank you.
Yeah.